Hey everybody, it's Mr. N here, and we're going to take a look at the next section. And this is on derivative tests, how to determine things, whether increasing, decreasing, how we can determine the shape of a graph. So let's take a look at this. First of all, we have here the slope of the tangents tell us which direction the graph is heading. So that's pretty obvious. If I have a graph that looks like this, and these slopes are pointing upward, so the graph is increasing. Now, over here at the top, I end up with a horizontal tangent. So right up there at the top, this graph, this curve, is neither increasing nor decreasing. So these tangents are all pointed in a positive direction, so it's increasing. These tangents are all pointed in a negative direction, so it's decreasing. So that's what we can take a look at there just visually, and so then we can write this out and we can say, if f prime of x is greater than 0 on an interval, then it's increasing. If prime of x is less than 0 on an interval, then it's decreasing. That's the simple basics of it. So now let's see if we can determine if we have a polynomial here where it's increasing and decreasing. So let's go ahead and do this example. So this one says determine where f of x equals x cubed minus 6x squared plus 9x plus 1 is increasing and decreasing. Since we said that if the slopes are positive, we can determine increasing, and if the slopes are negative, we can determine decreasing, we need to find the slopes. How do we do that? We take the derivative. So let's go ahead and determine f prime of x, and over here, that's what it told us to do, take the derivative. So this becomes 3x squared minus 12x plus 9. We're going to set this equal to 0 because I need to know the points where it is not increasing or decreasing, where there are possibly horizontal tangents, and then I can determine where it's increasing, where it's decreasing as far as being positive and negative, and I'll show you how to do that. And the method I'm going to use is called a number line method. This is the best one. There are other methods, but this is the one I want you to use. All right, so over here we're going to say 0 equals 3x squared minus 12x plus 9. I can factor out a 3. And I'm left with x minus 3 times x minus 1. And then I end up with x equaling 1 and 3. And here's what I want to do. These, as we learned previously, these are critical points, right? So we've learned what those were. But what I want to do with these critical points now is I want to put them on a number line. And I'm just going to test the intervals. So let's make this a little bit better, a little bit straight. I can't do anything today, seems like. All right. My line's not so straight, but we'll go ahead and deal with it. Here is 1, there is 3. Okay, so now let's take a look here. If I pick a point between 1 and 3. Suppose I pick a point. So these are the critical values, right? So suppose I pick a value between 1 and 3, somewhere in here. So let's pick 2. And I'm going to put 2 into my f prime of x, right? This is an f prime of x number line. What I want to do is I want to determine if that value is going to be positive or negative, because I need f prime of x to be greater than 0 to be increasing, and I need f prime of x to be less than 0 to be decreasing, which is what we had set up here. So let's take a look here. When I put in the value of 2, f prime of 2, now if you factored correctly, you could just put it in here, because you're just looking to see if it's positive or negative. You don't really need the full answer. You're just looking to see if it's positive or negative. If I put in here, I get a negative times a positive, which gives me a negative value. So all I'm just doing is seeing if this is positive or negative, because I just want to put these as negatives right in there. You could have certainly used the f prime of x version. It doesn't matter. I'm just showing you a little shortcut here. Now pick something between, or that's less than 1, 0. If I put 0 in here, right, I get 9. If I put it in here, look, I'll get 0, which is a positive number. I'll get 0, I'll get a negative, 0, I'll get a negative. Negative times a negative gives me a positive. So f prime of 0 came out to be a positive number. So in this region, I will have positives. And then I'll test something greater than 3, like f prime of 4. And I will do that, and I will get positives there. Just think of it over here. Positive, 4 minus 3 is positive, 4 minus 1 is positive, positive times positive, I will get positive values. So here's my number line, and that's what's going to help me solve this. So now, I know my critical points are 1 and 3, right? This is when the function was 0. Now, I know it's going to be increasing when the slopes are positive, so that's from negative infinity to 1. union 3 to infinity. Now there's another way you can write this. You could just say x less than 1 and x greater than 3. It'll be decreasing when x is between 1 and 3, and the other way of writing it is, oops, I need the open interval, 1 comma 3. So you can write it in either notation, whether you want to use the interval notation or the inequality notation. Okay, so with the brackets I meant. All right, so that's that. If you want to graph this, you can quickly sketch a graph of this. You know the critical points are at 1, 1, and then 1, 2, 3. So we're going to get either like a maximum or minimum here. You'd have to plug it back in and determine what the y value would be. But I should say possible maximum or minimum. I'll explain that in a little bit. And then over here, when you put in 3 into the original equation, you would get a value that's somewhere down here. But anyway, this graph would look like this. Now let's take a look. Between 0 and 1, or between infinity and 1, I should say, it's increasing all the way up. It stops right there. Between 1 and 3, it's decreasing because these slopes are negative. So between 1 and 3, it's decreasing. And then greater than 3, it continues to increase again. All right, go ahead and do that second example. I would suggest pausing the video, trying to do it on your own, and then I'll show you the answer. All right, so here's what we have. We need to take f prime of x, set it equal to 0. So this would give me 12x cubed minus 12x squared minus 24x. Set this equal to 0. You could take 12 and an x out, and you're left with x squared minus x minus 2. And then you can factor this one into x minus 2 times x plus 1. So all our critical points are going to be 0, 2, and negative 1. And what am I going to do with these critical points? I will put them on a number line, and I'm going to test them on f prime of x. So here's 0. There's 2. Oops, I should have started with negative 1. I should have seen that. So we'll say that this is at negative 1 here. There's 0, and there's 2. These are the intervals I am going to test. So now I put in a number right here that's less than negative 1. So say f prime of negative 2. I will get a negative value. Again, you can just quickly put it into here. It's negative 2, that's a negative, and that'll be a negative. So negative times negative times negative gives me negative. And then between 0 and 1, you'll get a positive. And then between 1 and 2, put in 1, for example, you'll get a negative. And then greater than 2, you'll get a positive. Now, some of you may be saying, hey, will it always alternate like this? No. It depends on the function. Polynomials will typically alternate, but if it's just an inflection point, it won't. So we'll talk about all that later, but no, it will not always alternate. You need to test it. Okay, you need to test every region. So over here, now I know where it's increasing and decreasing. I will write the two notations again. It's increasing from negative 1 to 0 and from 2 to infinity. It's decreasing from negative infinity to negative 1 and the union from 0 to 2. If you wanted to write it with the interval notation, it would be increasing from negative 1 less than x less than 0 and x greater than 2. It's decreasing when x is less than negative 1 and 0 less than x less than 2. All right, so now what does all this help us? Well, take a look. We have this first derivative test. Suppose c is a critical number on a continuous function f. If f prime changes from negative to positive, then I have a local maximum. If f prime changes from negative to positive, then I have local minimum. If there's no sign change, there's no local maximum or minimum. Wait a minute. Take a look. Here's what I'm saying on this one. I'm going to use a different pointer tool. So take a look. I'm going up. These are positive slopes. I get here, it's a horizontal slope, and then I go to negative. So look at it, made a maximum. These were positive slopes on this side, these were negative slopes on this side. So if I change from positive to negative, I will get a maximum. On a number line, it looks like this. This is your critical point. You went from positive slopes to negative slopes. You went positive, negative, it made a maximum. Look at the next one. You went from negative to positive. So right here, you went from negative slopes to positive slopes. It made a minimum. So on a number line, this would look like this. There's your critical point. Okay, and then we went from negative slopes to positive slopes. So you could say negative slopes to positive, it made this minimum. And take a look at this one. Here's your horizontal tangent. This ended up being your critical point. And here you just went from positive slopes and you continued on to positive slopes on a number line. This would be your critical point, and you would go positive slopes to positive slopes. Nothing changed, so it's not a local maximum nor a local minimum. That is our first derivative test. I always want you to use these number lines because it's going to help us later with other things that we're going to do. Look at what we got next. Over here, the importance of the first derivative test right there is that it's going to help us find maximums and minimums. So the importance is that it's going to help us find all those maximums and minimums. All right, look at this first example. Find the local maximum minimum for this. So I will have you pause this. I'm going to have you try it and see if you can get the right answer. So for this first one, we'll start by finding the critical points, and we will take the derivative. So let's go ahead and do that, and we're going to have f prime of x over here. This is going to be 3x squared minus 12, and we will set that equal to 0 to get the critical point. So 0 equals, and I could take a 3 out, so I'll get x squared minus 4. So 0, and then here this will be x minus 2, x plus 2. So my critical points are x equals plus or minus 2. So I'm going to put these on a number line and see what happens. So here's my number line. There's negative 2, there's positive 2. And this is f prime of x number line, and I'm going to test the regions in between. So I pick a value less than negative 2 right here. So if I pick like negative 3, negative 4, negative 5, it doesn't matter. I will get a negative times a negative. So that ends up being a positive value here. Then I pick something in this region, such as 0. I will get a negative times a positive, which gives me a negative. And then I will pick something right here, such as 3, 4, 5. And I will end up with a positive times a positive, which gives me a positive. So now looking at this, I know that I am increasing on the interval from negative infinity to negative 2, and I am increasing on the interval from 2 to infinity, and I'm decreasing on the interval from negative 2 to 2. But since I'm just looking for local maximums and minimums, not absolutes, it just says local here. So I'm going to examine this one. This gives me a positive slope on this side, and then it changes to a negative slope, so that creates a maximum value. Over here, negative slope to positive, this creates a minimum value. So I have a maximum, a local maximum at x equals negative 2, local minimum at x equals positive 2. If you wanted to know the actual value for those, you would plug it in, and you would get the values would be 11 over here, and for this one it would be 8 minus the 24 minus the 5, which would give me negative 21. So these occur at negative 2, 11, and to negative 21. All right, let's take a look at the next one. Let's start by graphing this, because this is a piecewise function. So I'm going to graph it right here. Let's do this first. And I will graph it right here. And this becomes a parabola. That first part, it's actually open circle, and goes this way. On the second part over here, we're at 1, and it is a closed circle, and it'll go that way. Notice there's no continuity here. It's discontinuous at 1, or at 0. So not continuous at x equals 0. But can we still find any local maximums and local minimums? Yeah, we can. If I take the derivative, I'll get negative 2x when x is less than 0, and I will get 2x when x is greater than or equal to 0. So there's only one critical point. The critical point is at x equals 0, and you can see that. Remember, critical points are where it's undefined or it equals 0. So that is a critical point. If I were to test this, and if you were to test this on a number line, here's 0, you would get positive slopes here, you get positive slopes there. You can take a look at the graph and determine that. So this is indeterminate. You can't determine anything from it. But when you actually do look at the graph, you'll see that there is, right here, that is a local minimum. So there is a local minimum at x equals 0. So this is the only spot where you will have that local minimum. The key here is to remember that you can have extrema even if not continuous. What we could do is you think of the extreme value theorem. So in this case, you have to take a look at this graph and you have to determine it. All right, let's move on. Over here, we have concavity now. When we deal with concavity, we can take a look at the second derivative, and it'll also tell us with info about the function. Concavity, if it's concave up, that means if the graph of f lies above all the tangents on an interval. Now, you're used to seeing concave up just by looking at a parabola, and you would say, oh, okay, it's like that, that's concave up. Concave down would look like this, right? So basically, though, here, by this definition, all these tangents are below it. So the graph is completely above the tangent lines. Just like here, these tangent lines are above it, so the graph is completely below it. So that's how we define it. And here's our concavity test. If f double prime of x is greater than 0, it's concave up. If f double prime of x is less than 0, it's going to be concave down. An inflection point, and often we abbreviate this with IP, is where it does change concavity. So if you see something go like this, then like that, right at this point right here, it's going from concave down, right, to concave up. So that's where it changes right here at that point, and that's going to be called an inflection point. The second derivative test, okay, suppose that f double prime is continuous near C. Then if f prime of C equals 0 and the second derivative is greater than 0, we know it's concave up. If f double prime of C is equals 0 and the second derivative is less than 0, it's concave down. A lot of teachers will teach you the second derivative test in this manner, so you're going to take the second derivative, plug in 0, and see what happens. I'm going to go ahead and have you do it on a number line with the second derivative, and that way you can compare it to the first derivative, so that way you can see all the intervals increasing, decreasing, and the concavity. All right, so steps to find the max or minimum. First, find, in this method, first find the derivative, then set it equal to 0, get your critical points. Plug in the critical points into the second derivative to determine concavity. F double prime of x greater than 0 is concave up minimum. If it's less than 0, concave down, it's maximum. That's the second derivative test. But again, I'm going to show it to you a little bit different. So let's move on to that now. So let's take a look at what we have on this page. And on this first example, we need to, from the graph of f prime, this is giving us a graph of f prime. So it's important to note that it's saying that this is an f prime graph. We have to determine the critical numbers, the intervals on which it's increasing, decreasing, and find any relative extrema. Now, on this first example, it doesn't, we'll go with what we have here. Okay, so over here, this is, remember, an f prime graph. That's important to note. How do we get critical numbers? We take the derivative and set it equal to 0. So now I need to know where the zeros are for this function. The zeros are right here, and right here. We'll say that this is at -4 there. So we have the critical points for part A at x equals -4, 1/2, and at 3. So now, if I put this on a number line like that, this is 3, there's 1/2, there's -4. Notice that this is above the axes here. So you're looking at these, this is above the axes. These are going to be positive slopes. Over here, the values, this is f prime of x. And these values for f prime of x are less than 0 because it's below the axis, so these are negative. Then over here, it's 0 again, and it turns positive, and then over here, it goes back to negative. So I'm looking at where they are in relation to the axes because I'm looking at an f prime graph, not the original. So I'm not looking at the slopes. These are the slopes. The slopes are positive on this side, negative, positive, and then back to negative here. So that tells me for part B, it's increasing from -infinity to -4, union 1/2 to 3. It's decreasing on the interval from -4 to 1/2 and 3 to infinity. Okay, then we have to find relative extrema. Relative extrema is if it changes from a positive to negative, negative to positive. Well, look, here's a positive slope to a negative slope, so we have a relative maximum at x equals -4, and we have, over here's another change from negative to positive, a relative minimum at x equals 1/2, and then again from positive to negative we have a relative maximum at x equals 3. So there's parts A, parts B, and part C for that problem. Let's see if we can squeeze in the next one over here. So taking a look at this, we have, for part A, we need to determine the critical points. Critical points, remember, is when f prime of x equals 0, or if it's undefined. So for this one, we're looking for that undefined point as well. So this happens at x equals 0 and 2. At 2, we get a 0. Remember, this is a f prime of x graph, and this is the undefined point. So critical points are where it's undefined or if it equals 0. All right, so now let's determine where it's increasing and decreasing. This is all above the axes right here. So if I put this on a number line, which I will do like this, right? Here's a critical point at 0. Here's a critical point at, let me put this below it. Here's a critical point at 2, okay? So we've got our two critical points right here at 0 and at 2. And I'm just doing the number line here. These are positive slopes all the way to 0. Then over here, I'm below the axes, okay? So these are going to be negative slopes. And then over here, I'm above the axes. So these are going to be positive slopes at this point. So it's increasing at, well, we don't need the at, let's put in the interval. It's increasing when x is less than 0 and x is greater than 2. So you could say x less than 0 and x greater than 2. I'm doing the inequality notation this time so that you could see it a little bit different. Again, I could have said over here from -infinity to 0, union from 2 to infinity, but I'm just doing a different notation for you guys. So then it's decreasing over here from 0 less than x less than 2. So that's where it's decreasing. All right, so then let's just do step C. I'm going to erase this right here. And then we'll put in part C right here. And part C is any relative extrema. Well, we're taking a look right here. We go from a positive slope to a negative slope. So we have a relative maximum at x equals 0. And then we've got from here to there, we've got a relative minimum at x equals 2. So those are the spots where it changes from increasing, decreasing, so those will give me my relative extrema. All right, let's move on to the next problem. See if I can, again, squeeze that in there. I should have given you guys a little bit more room here to write, but that's okay. So let's try this. And it says, this is my f prime graph again. So we need to determine where it's the critical points. And the critical points here are going to happen. We'll say that that does cross the axis at 0. Let's just say it crosses here at -2 and 0, and then this is at 1. Or actually, that's at 2. So over here, my critical points are at x equals -2, 0. I'm telling you that crosses through there, and +2. But there's one more. Where's the other one? At x equals 1 also, because that's undefined, so that gives us a critical point. So again, just a reminder, the critical points occur where it's 0, the derivative f prime of x equals 0, or undefined. All right, so for increasing, decreasing, I'm going to put these on a number line. I'll do it like I did the other ones, right above over here. Let me erase this thing. And let's take a look. So my critical points are at -2, 0, 1. Put the 0 down here, and at 2. Okay, so those are all my critical points, and let's determine what happens in between. Over here, I am below the axes, so these are negative. I'm above the axes, and then here at 1, I cross to go below the axes. At 0, sorry, I cross to go below the axes. Then at 1, I'm back up above the axes, but then at 2, I stay above the axes. So those are all the things that is going on there. So we are increasing from -2 to 0, and from 1 to 2, and from 2 to infinity. Notice I had to write this because here at 2, I'm neither increasing nor decreasing, so I had to write it a little bit different. And then it's decreasing from -infinity to 2, and from 0 to 1. All right, so that means it's in this region right here. -infinity to -2. Oops, I didn't put a negative on that. And from 0 to 1, it's below the axis. So those are the two spots where it's below the axis. The graph is above on the other ones, so that's where it is increasing. Okay, and now let's do the third and final part on this one. And we're going to find the relative extrema. So we're going from over here, we're going from negative to positive, so that gives us this situation from negative to positive, and then positive to negative, negative to positive, and here it's positive to positive, so nothing happens. So we have relative, this is for part C, relative maximum at 0, and relative minimum at x equals -2, x equals negative, I can write that in, -2, and at 1. All right, so let's move on to the next problem. The next problem, we're finding the local extrema. So over here, that means we need to find any local maximums or minimums, so we're going to do that same process that we just did up above. So let's do this first one, and here we got f of x equals -x to the third plus 3x plus 5. So the first thing we're going to do is we're going to take the derivative, set it equal to 0 to get our critical points. So over here, I set this -3x squared plus 3, this derivative, equal to 0. I could take out a -3. I'm left with x squared minus 1. So then I end up with x minus 1, x plus 1. So my critical points are at x equals plus or minus 1. So that's what I need to test. So let's go ahead and test these. Over here I have -1, I have 1. So now I'm going to test the regions. Remember, you have a negative right out here. So if I put a number in here, -2, I will get negative, negative, and a negative. This region will be negatives. Now, pick a number such as 0 for this region. I will get a negative, and a positive, so that will give me positive values. And you pick a number in the next region, you will get negatives. So here we go from negative to positive, positive to negative. So we have a relative maximum at, and I'm going to give you the whole coordinate this time. It's going to be 1, 7, and a relative minimum at 1. Oops, that's going to be -1, 3. So those are the maximums and minimums, and I gave you the coordinates this time, not just the x value. And the way I did that was I just took the x and I plugged it in here and found the 7. Took the x, plugged it in here, found the 3. So there's the relative maximum and minimums. I'm not going to do the inflection points on this one. I'll do them on the second one. I'll show you how to do inflection points on the second one and on examples 6 and 7. Okay, so over here, on this next problem, we need to find the local extrema again. So here we have f prime of x equaling 3x squared plus 6x, set it equal to 0. You could take out a 3 and an x, and you're left with x plus 2. So your critical points, x equals 0 and -2. I'll put these on a number line. There's -2, there's 0. I'm going to test regions in between. So I'll put a number between smaller than -2. I put in, say, -4. I'll get negative times negative. Those will give me positives. I'll put one like -1 in. I'll get negative times a positive. That'll give me negative. And I'll put a larger number in, greater than 0, such as 5. And that'll give me positives in this region. So I go positive to negative, negative to positive. So this is going to give me my max. This will give me my min. So I have a relative max at -2, comma, let's plug it in and find out what that would be. That would be 2. And a relative minimum at 0, comma, we plug that into our original here, and I'll get -2. So those are the relative maximums and minimums on this one. And let's find inflection points. So how are we going to find inflection points? I'm going to take the second derivative this time. Okay, so I want to take the second derivative and set it equal to 0. So I have this as being my derivative right here. So the second derivative would be 6x plus 6. Set it equal to 0. And you will get x equals -1. So this is a possible inflection point. You don't know until you test it. And how do we test it? Well, we test it the same way we did before, but this time in the second derivative. It's kind of like my possible critical point for the inflection point. I need to see if it changes concavity. So this is going to tell me if it's concave up or down when the second derivative is greater than 0 or less than 0. So over here, I pick a value that is smaller than -1, -5. Okay, and I put it in here, I will get negatives. I pick a value that's greater than -1, 0. I'll get positives. Notice it changes concavity. It goes from a concave down to a concave up. So since it changes concavity, that is an inflection point. So I have a point of inflection at -1, comma, you could plug it back into the original again, and you'll get 0. And that's how we get our inflection points. All right, so let's continue with that concept and do the next one where we're going to find these inflection points. So for this first one, let's find the inflection points by taking the derivative. So what I want to do, though, is I want to rewrite this. It's easier if I say 4x cubed minus x to the 4th and take the derivative that way. Okay, so I take the derivative, I get 12x squared minus 4x cubed. Since I'm finding the inflection points, I'm not concerned so much with the critical points here, although I can get them. But let's go ahead and just go straight to the second derivative, and that'll give me 24x minus 12x squared. Set this equal to 0, and, 0 equals, I should say. And over here I could take out a 12, and I'm left with 2x, 12 and an x, and I'm left with 2 minus x. And so my possible inflection points are when it's 0 or undefined, so that's going to be 0 and 2. How do I know if they are? I need to test them. There's 0 and there's 2. And I need to test them in f double prime. So I'm going to pick a number smaller than 0, say -1, and I'll put -1 in each of these. And I'll get a negative times a positive, that's a negative. I'll pick a value here that is between 0 and 1, say 1, and I'll get positive times a positive, that's going to give me positives. And then a value greater than 2, so say we got 3, that'll give me positive times a negative, negative. So I do change, this is concave down, this is concave up, there's concave down. So I do change concavity on each of these, so all of these are inflection points at, and we'll list them, 0 comma something and 2 comma something. When I put in 0 into the original equation, I will get 0. When I put in 2 into the original equation, I will get 16. So those are my inflection points. Okay, so for this next one, this should really say, and we're going to change it, this should be tangent of x, it should be like this, to the -1 power. So you don't confuse it with the inverse on that one. So f prime of x will be -1 tangent x to the -2 times the chain rule, secant squared x. F double prime of x will end up being, now we got to do a product rule, -1 tangent x to the -2 times 2 secant x times secant x tangent x plus, now the second part, secant squared x times 2 tangent x times secant squared x. All right, you want to know when this will be 0. Well, when the tangent is 0 or the secant is 0, that's when it will be 0. And that'll happen at 0, at x equals 0. So when you plug that back into the original, you'll get 0. So 0 comma 0 is an inflection, and you test it on each side of it, and you will get that change. Okay? So 0 comma 0 is an inflection point. Here when you plug in a number, you're going to get something that's going to be concave up, and here you'll get concave down. So you can always test it like that as well. All right, moving on to the next problem. Let's move this up and see what we got here. On number 8, it says use the behavior to sketch a graph of the continuous curve y equals f of x. So let's draw an axis here. So we've got our axes, and we're going to take a look at what's going on here. It says, here's my x and y, and here's what's happening with the curve. When x is less than 2, it's falling and it's concave up. So x less than 2 tells me that falling means decreasing. And again, these answers can vary. So I'm going to put 1, I'm going to put 2 right there. And it's falling means it's coming down but concave up, so it looks like this. Right? I could have put it down here. Right? I don't know anything yet, so I'm just kind of trying to piece this together, and then we'll figure it out as we continue on. So let me erase this. Alright, so now taking a look at the next thing, it says when x is 2, I got to point at 1. So I do know that it should have been right here. So when x is 2, I do have a point at 1. Let's see if there's any other points I know for sure, because that'll help me. So typically what you want to do is look for coordinates that you have, because then it kind of pieces things together and gives you some points to aim towards. So as I mentioned, at 2, 1, I did have a coordinate there, but this was a horizontal tangent. So I knew, and I'll do it in a different color, that this had to flatten out here. So yes, it was falling, and it's going to go to this point. Okay, then at 4, 4, right here, I have an inflection point. So it's somehow going to change concavity there. So concavity. All right, and then at 6, 7, 1, 2, 3, 4, 5, 6, 7, right there, I have another horizontal tangent. All right, so let's see what happens here. Let's do that in red. Okay, and let's see what happens now in between these. So we did this one, okay, we're going to come towards this horizontal tangent here, so that means this did fall and flatten out right there, so we did that. Then between 2 and 4, it's going to be rising, so and concave up again, so it's still concave up, but now it's rising, which means it's increasing, so I'm going to put it in that direction. And then at 4, 4, we have an inflection point. The inflection point means it's going to change concavity. So if I was concave up, now I'm going to be concave down like this. And then between 4 and 6, it's rising, so it's still going up, but it's concave down until it reaches this horizontal tangent right there. So that's what that'll look like in that region. Concave up here, then concave down there. All right, and then greater than 6, it's falling and concave down, so it's in that direction. So that's what the sketch of this graph would look like. And again, answers may vary a little bit, but it should pretty much look very similar to this. Moving on, let's see what we got here. For this next one, it says, find the absolute extrema of f and where they occur. Find any points of inflection and sketch a possible graph of f. So it's very similar to what we just saw. Now it's going to be in a table format. So remember what these things tell us. These are just going to be points on the graph for the function. And over here, if it's positive in this region, means it's increasing, it means it's going up, right? It's above the axes, below the axes. Here, the derivative over here will have a value of 3. That means it's a slope of 3. That means at 1, it's going to be a slope of 0. That slope doesn't exist. Over here, the slope is negative 3. In this region, the slopes are positive. This region's negative and negative. Second derivative is going to give us concavity. So this tells us these are the slopes. And this tells us if it's increasing, decreasing. And then the second derivative will give us the concavity and any possible inflection points. All right. For part A, since we have to find the absolute extrema, I need to test endpoints as well. And I need to test the endpoints on what I am given. So over here, let's find out what the critical points are first. Okay, so critical points when f prime of x equals 0 or undefined. Okay, so my critical points are at x equals, I'm taking the derivative when f prime of x equals 0, right here, at x equals 1, undefined right here, at x equals 2. Those were my critical points. So for part A, I need to test f of 1, f of 2, because those are my critical points, and I need to test my endpoints, f of 0 and f of 3. Okay? At f of 1, I get a value of 2. At f of 2, I get a value of 0. At f of 0, I get a value of 0. And at f of 3, I get a value of negative 2. So this is my minimum, and that's my maximum. So those are the absolute minimums and absolute maximums. So the absolute maximum is at 1, 2, and the absolute minimum is at, this will be at 3 comma negative 2. Those are my absolute extrema for part A. For part B, let's take a look at what we've got to do. We got to find points of inflection, find any points of inflection. So to find possible points of inflection, I take my second derivative, set it equal to 0 or undefined, and that's where I'm looking at. So the second derivative will be 0 at right there. So I need to, these are possible. I won't know till I test them at x equals 0, at x equals 2, and x equals 3. These are possible inflection points. Now what we could do is we could put these on a number line. We could have put this first one on a number line also, where we put our critical points in at 1 and 2 and test the intervals in between by looking at f prime, right? If I have my interval between 1 and 2, this is negative. If I have my interval between 0 and 1, this was positive. And if I've got my interval between 2 and 3, this was negative on the first derivative. All right, so I knew that I had to have some sort of relative maximum here, and then I had to test it against to see which is the absolute. So that could have been a way to do it there. So we could do the same process on this one. So if I take a look at my second derivative, I'm going to put my possibles, 0, 2, and 3, and I'm only going from 0 to 3, so I don't need to consider what's happened prior to that. So if I plug these into f double prime, and I'm looking at the intervals here, f double prime, the interval from 0, right here I'm looking, to 1, let me point to where I'm looking right there, these are negatives. And then from 1 to 2, it's still negative. Okay, so these are all negatives in here. And then from 2 to 3, it tells me that there's negative again. So basically, there's no sign change. So there is no inflection point on this one. So these are all going to be concave down. From the interval from 0 to 2, it'll be concave down. From 2 to 3, it'll be concave down. So that's going to be interesting on how we have to sketch this. So that's for part C, where we have to do the sketch. And let's do that. And let's put a different color in here again. And here's part C, where we need to sketch the possible graph. So if I draw my axes here, and I've got over here, I know there's an absolute, right, maximum at 1, 2, 1, 2. This is an absolute maximum. I have an absolute minimum at 1, 2, 3, negative 2. This is my absolute minimum value. Now I got to find out what happens in between. Okay, in between, taking a look here, I see that this function is increasing. Okay, it's above the axis and it's increasing. Above the axis increasing means it's going to go like this. Let's use a different pointer. So above the axis increasing, it'll go like that. And it's concave down, so it's going to have curvature like this. And then I'm taking a look here. From 1 to 2, I'm still above the axes, but now I'm decreasing, and I still have concave down curvature. Then from 2 to 3, I'm below the axes, I'm decreasing, and I'm concave down, so I'm going down like this. So basically this kind of is a funky graph that goes right here, because that's a critical point. It goes like this. That whole thing is going to be concave down with the absolute right there. And then it's going to be like this. That gives me, again, something that's concave down. It's kind of almost like sort of a kink right there, because the derivative doesn't exist at 2. So when it doesn't exist, it's going to be sort of like a kink because it's continuous, and that's what happens. So that's what this graph will look like. All right, moving on to the next problem. It says, if f of 0 equals f prime of 0, which equals f double prime of 0, which of the following must be true? For the first one, it says there is a local maximum of f at the origin. Well, we can't quite prove that because just because they all equal to each other, we don't know that is a local maximum because we don't know what that equals. We just know that f prime of 0 equals that. So we cannot conclude on that one. There's a local minimum. So if we can't do the maximum, we can't conclude the minimum. There is no local extrema. Again, we don't know. It could be. It could be. There is a point of inflection. Well, we don't know what this equals, so we can't do it. There is a horizontal. We do know that there will be a horizontal tangent since f of 0 equals f prime of 0. So we do know that this is the only thing that we can conclude on this problem. Okay, moving on. Sketch a graph of y equals f of x that has the following properties. Alright, so let's take a look at what we have here. I've made an axis real quick, and we're taking a look over here. F of negative 2 is 8. So we're going to put at negative 2, 1, 2, 3, 4, 5, 6, 7, 8. We know there's a point there. F of 2 is 0, so we know there's a point there. F of 0 is 4, 1, 2, 3, 4. We put a point there. So far we've got this, we've got this, we've got this. And then f prime of 2 equals f prime of negative 2, which equals 0. So that means these are horizontal tangents because these derivatives equal 0, so these are horizontal tangents. So I do know that it flattens here and it flattens there. Let's go ahead and do that in a different color. Flattens and flattens. Okay, then I have here f prime of x is greater than 0 for all absolute value of x is greater than 2. So that means between 2 and negative 2 right there, it's going to be the slopes are going to be positive. It's going to be greater than 0 from x is less than, I should say, negative 2, and x is greater than. So the slopes are positive, so that means I'm going upwards here, upwards there. On the next one, it says for less than 0 is less than 0, so these slopes are negative, slopes negative for between negative 2 and 2. So these are going to be down like this. Absolute value of x less than 2 means this is going to be between negative 2 and 2. Over here, it's less than 0 for x is less than 0. And this is on the second derivative, so this is concavity. So it's concave. Concavity will be, it'll be concave down when x is less than 0. So that means this, we know, will go like that, hit the maximum there. Concave down, and the whole time will be concave down like this. So that kind of narrowed that up, and then concave up when it's greater than 0. So that kind of narrowed in what this graph would look like. So there's a concavity that's up and down. So that's just a quick sketch of this possible graph. Okay, next one. Which of the following conditions would enable you to conclude that the graph of f has a point of inflection at x equals c? All right, looking at this over here, there is a local maximum of f prime of x at c. So a local maximum will look like that. But remember, this is talking about f prime of x. So right, f prime of x, that gives me a horizontal tangent. So that's f double prime equaling 0. Right, because this is f prime of x has a maximum, so it has a horizontal tangent for the second derivative. That's kind of confusing. But yeah, that for sure is there. Let's take a look at the next one. F double prime of c equals 0. No, remember, the second derivative equaling 0 gives you possible. You have to test all the possible ones on the number lines to see which work. Just like this. This yields possible. Right? So we still need to test all these. So this is no. There's f prime of x has a sign change at x equals c. Again, this is talking about the first derivative, right? If we have a number line here and we have f prime of x, the sign change will only yield increasing, decreasing. So that's a no. And then f is a cubic polynomial and c equals 0. On this one, no, we don't know if it's that. So the only possible solution is A for this. Alright, so thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.